let's do this other notes where we're going to do an example. We're going to do a couple different examples of calculating a confidence interval. So on the formula sheet, like on the first page, on the front page, at the bottom, it has confidence interval equals statistic plus or minus critical value times standard error. So we're going to talk about what this is. And so remember from the first video, a confidence interval is like we get a point and then we're going to put a margin of error on the sides. So that's like what this is. This is your point, and then this value over here is your margin of error. So that's kind of, we're going to get into that and how do we get those values and stuff. All right, so let me make up this example. It's kind of a bummer that I'm missing this one because we'd normally buy some Hershey Kisses, and the thing on this one is having a bunch of Hershey Kisses in your hand and rolling them onto a table and seeing how many land flat, like flat side up. And so we would have done a sample of 50. So I'm just gonna make my own stuff up and we'll do it. All right, but I'm gonna actually talk about number 2 first, then I'll do number 1. So on number 2, what's our population and what's our sample? So our population in this case, we're talking about Hershey Kisses, and so our population that we're trying to talk about is all Hershey Kisses. Like I want to generalize this to every single Hershey Kiss. And what we did, or what we would have done, is we would have sampled 50 Hershey Kisses. All right, and then a parameter in a statistic is like what number were we looking for from the population? What number from the sample? So what we were trying to do was find the proportion of the Hershey Kisses that would land flat. So our statistic is going to be like our sample proportion. So let's say that I did this, and out of 50, I rolled Hershey Kisses onto a table, and 21 out of 50, or 42% of those Hershey Kisses landed flat. All right, that's our statistic. The parameter would be like, we don't know, but the parameter would be P, which is like, if I threw like all the Hershey Kisses and forever and ever and ever on the ground, like what's the actual proportion that would land flat? Like we have no way of knowing this. So we're just gonna estimate this. So actual proportion landing flat versus this is like a sample proportion. So we're gonna use our sample. So we use sample to estimate population. So I have no idea how to get the actual proportion, so I'm going to use my sample of 42% to estimate what is the actual proportion of all Hershey Kisses of all time throwing on the ground, the percent that would land heads up. All right. And so we got a p-hat of 21 over 50, or 42%. This can also be called a point estimate. So like this is like our starting point, 42%. Like a point estimate is like your p-hat, or if you're doing means, it would be your sample mean. So your sample proportion or your sample mean. That's what that is. On the formula sheet, it would be the statistic. So the point estimate right here is the statistic, which in this case was, we're going off 42%. So like that's our starting point there. All right, so let me go back. So what I'm gonna do is I'm actually gonna skip through kind of some of these conditional things. And I'm going to go straight to number 9. And we're going to get the conditions on our second example. But I want to give you just the problem first, and then we'll go over some more of the details. And if needed, like, of course, we'll just keep going through them on Tuesday and further lessons. But let's just get into how do we calculate it. All right, so like on our formula sheet, I have my point estimate, my statistic. Now I need to plus and minus a margin of error. So like if you remember, a confidence interval is you get a point and then I want to get a wide range of values, and so I plus or minus a certain distance. So this is how we get our plus or minus value. It is critical value times standard error. So let me write that. So margin of error is critical value times standard error. All right, and so on your paper, we're going to be looking at number 9 and 10. So if you want to write this, somewhere different, you're good. Let me just explain what a critical value is. So a critical value is just our z-score. And so a z-score is what number of standard deviations are you from the mean? Are you negative 1.2, 2.38 standard deviations above? Like, what are you? So a critical value is your z-score, and it comes from your percent confidence. That's where it comes from. So we're going to get into that on this problem. And then let me tell you about standard error. So standard error is the same thing as standard deviation, except it's for p hat instead of p. So let me show you on your formula sheet, and it says it on the formula sheet, the same thing. So on the formula sheet, on the back side where we have our formulas, you can see here is the standard deviation, and then over here it says the standard error. And the only difference between these two standard deviations is that this one is using p 1 minus p, and this one is using p hat 1 minus p hat. So standard error, you use that when you don't know the p. So you use that when you don't know the p. So like in this case, if you remember, we have no idea what the true proportion of Hershey Kisses, all the Hershey Kisses in the world. All we know is the sample proportion. So it's just another word for standard deviation, except it's for p hats. All right. So how do we get, here, let's do standard error first, because that one's easy. All right, so the formula, so I'm following the formula for standard error. On the formula sheet, it says do p hat 1 minus p hat over n, right? Which was 50. We did a sample size of 50. All right, so we got that. We know how to use a formula sheet. How do we get our critical value? So we're doing a 95% confidence interval. So 95%. All right, what that means is when you do your normal distribution, what it's saying is that we want to be able to capture 95% of our data. That's what a 95% confidence interval means. It means over many, many trials, we expect about 95% of our intervals to contain the actual thing. And so the way you do that is you set up a normal distribution that contains the middle 95%. All right, so how do we get our z-score from this? And so the z-score is right here, like what is the z-score at that 95%? But we know that a z-score chart, so the chart got my fancy purple here. The z table always goes from this value all the way less than, like for infinity to the left. So what value, what percent are we actually looking for right here if this is the middle 95%? So if you've got 95%, kind of a tricky part about getting the critical value is that you have to think about how much is on the tails. If 95% is in the middle, we have 5% on either end. And so that means there's 2.5% over here, 2.5% over here. And so this purple value is 95% plus 2.5%. So we're actually looking for the value of 0.975. So 97.5%. We're going to look at the z table. You'll get used to these. We use a lot of the same values. So just stick with me. So what I did, 95%, and then I put that in the middle, and there's 2.5 on the edge. So all the way to the left, 97.5. So what we're going to do is we're going to go to our z table, and we're going to find the closest value to 0.975. So I'm going to go to my z table, my z chart, and I'm going to look up in the middle values here the closest value to 0.9750. So I don't see it. It's a positive number. So let me look for it here. So 0.97, and it's actually a perfect number, 0.9750, which is at 1.96. So z equals 1.96 for a 95% confidence. Because remember, let me just draw it out again. 95% in the middle means 2.5 on either end. So we're actually looking for 97.5 as my number. All right, so my critical value, this is my critical value, my z-score of 1.96. So 1.96. 1.96. There we go. So what I'm doing here is I'm going to do 1.96 times the square root of 0.42 times 0.58 over the square root of 50. And what I got, and hopefully check this on your calculator, should be right, 0.137. So this is my margin of error. So that is my margin O error. Or of, same thing, margin of error, 0.137. So this is the value. All right, so let me go to the next one. So that's our margin of error. We're going to do another example, so stick with me. So find the 95% confidence interval, and we're going to use our statistic plus or minus margin of error. So our point estimate is our p hat. So to get my interval, I had 42%, but then we're plussing and minusing a margin of error of about 13%. So like I literally need to do 42% plus 13.7, 42% minus 13.7. So you get 0.557, 0.283. So you can write it like this. You can write it as 283,557, or you could say it like this, 28.3% to 55.7%. And so what this is this is like our answer, this is our interval. And what we think about this is that we're 95% confident that this interval contains the true proportion of kisses landing flat. That's what this means. Okay, we're thinking somewhere in this interval. So when you toss a coin or toss the Hershey Kisses onto the floor, somewhere within 28% to 55%. So that's not a very accurate. That's a pretty big interval, but we're 95% confident it's somewhere within there. So it's not the most accurate interval you've ever seen. And so let's go back to the first part of the lesson. How could we make this? So this wasn't planned, but this is a good spot. How can this interval get smaller? All right, so how can this interval get smaller? There's two ways. Number one is your sample size needs to do what? So if I want my interval to get smaller, the sample size, does it go up or down? Hopefully you're saying that it needs to go up. If I want this interval to get smaller, my sample size needs to go up. Or number two, if my interval is going to get smaller, if I want to be more accurate, I need to be less confident. So like 80% confident, 50% confident, whatever. Okay, I either need to be less confident or I need to do a bigger sample size. All right, so that's if you wanted your interval to get smaller. I'm recording. Okay. Awesome. Okay. All right. So if you want to get your interval smaller, you need to increase your sample size, lower your confidence. Okay. So what are the main points? So knowing your formula sheet. So knowing the formula. And so the formula, it says statistic. And so maybe I'll make a note as I do it. So a statistic is like a p hat or an x bar. So it says statistic plus or minus critical value times standard error. And your critical value is your z-score. And your standard error is basically your standard deviation, but with a p hat instead of p. Alright, and then finding the z-score is, remember, from your confidence. And the way you do that is you have your whatever your percent confidence is, and then you need to get this z-score, so you need to get all the percent forever this way. And so it's like point whatever. So like you need to get your tails one way or another. So our example was if it's 95%, there's going to be 2.5 on the edges, so it's going to be 0.97. Is what you're looking for. Alright. Cool, so that's an example. Let me do another one. And then we're going to be good. So we're going to try this with a different confidence level, different question. And then I'm going to add a couple things. So there's these things called conditions that we have to do. And if they're not met, then we can't do our problem. But if they are met, then we can do it. All right, so let's read our problem. What do you want to do when you grow up? According to a nationwide survey, a random sample of 1,000 kids under the age of 12, some kids want to be a ninja, dragon keeper, okay, dancing unicorn, and even an octopus, all right. 55 out of 1,000 kids want to be a doctor. We would like to use this study to find a 98% confidence interval for the true proportion of kids who want to be a doctor. All right, identify the parameter. The parameter is like the population number that we're looking for. So what are we looking for? It's right here. The true proportion of kids. So like the true percent of kids who want to be a doctor. That's what we're looking for. The true percent of kids who want to be a doctor. All right, so there's three conditions that need to be met for us to be able to do these problems. 3 conditions. And we're pretty familiar with all of them because we've been doing stuff like this. So some things that we've been putting in throughout the year will kind of start kicking in a little bit. So the first condition is that we need to have a random sample. Because if you didn't sample randomly, it could be bias. So basically, I'll make a note here, is like, we don't want bias, we don't want misleading stuff. So is this a random sample? So like every single time, did we do a random sample? So yes, it says random sample. All right. The second one is our data independent? Are we independent? So did we do things that are like our samples? Is this random sample of 1,000 kids, is it independent? Like, are those kids' answers given the opportunity to be independent from one another? And so one way that we've done this is that we want our sample size to be less than 10% of your population. Because if it is, that gives room for variation. So our sample size is 1,000. And is 1,000 less than 10% of kids age 12? Kids under 12. And I would say yes to that. There's probably more than 10,000 kids under the age of 12. There actually is guaranteed more than that. All right, and then the last one is going to be, is our distribution normal? So maybe I'll put it up here. Is the distribution normal? Question mark. All right, and so it was kind of, some people, it wasn't hit on as much on sampling distributions. It was a question on the test that some people missed. So is the distribution normal? So there's different ways to do it for P's and means, X bars. So for P's, to see if it's normal, you have to check is N times P and N times 1 minus P bigger than or equal to 10. So is your sample size related to the proportion big enough? So is it big enough? All right. So our sample size was 1,000. And what the heck is our P? So our P hat was right here at 55 out of 1,000 for, pretty sure that's 0.5, like 5.5%, 0.55 is your P hat. So you got to do 1,000 times 0.55, 1,000 times 0.955. So you get 55 and 9. Oh wait, that's wrong. 945. So that's 945. Thought that looked weird. That's 0.1 minus 0.55, 945. Alright, so that's yes, normal. So like that's normal. So we have to have, we don't want bias in our, we want a good sample. We want our sample to be independent responses, and we want our distributions to end up normal from our samples. So we need these three things to be true. Alright, so let's try and do our problem here. So find the critical value for a 98% confidence interval and calculate the interval. So we're gonna, what is our interval? So maybe let me write our formula, and I'll write it the way that it's seen on the formula sheet. Statistic plus or minus critical value times standard error. Alright, and so our statistic in this case is our p hat, which was 55 out of 1,000 kids. So 0.055. Alright, our critical value is our z-score. And so let me do this on a separate page. So we're wanting to do it for a 98% confidence interval. So that was pretty good. Pretty good picture there. Alright, 98% confidence interval. And let me use the purple again. We're looking for what is the z-score right there. What z-score is that? And so the z-score on the table that we use goes all the way less than. And so 98% means that there's 2% left over on the edges. So that means 1% and 1%. So that means we're actually looking for the value of 99%, so 0.9900. We're looking for the value closest to 99% less than on our table. So this is where we have to use our table. So I go to my table, erase my lovely markings there, and I'm looking for the closest value. And I'm going to warn you, some of these are split. I can't remember if this one is to 99.00. So this one, 98.98. I think 99.01 comes closest right there. So that would be at 2.33. So 2.33 is the closest value. So we're looking for the closest to 0.9900, which is this. So that's our critical value, 2.33. All right, so you can see it's different. Let me go back. It's different than this critical value of 1.96 because we have a different percentage. So this critical value is 2.33. And then times, so 2.33 times standard error, which is p hat times 1 minus p hat over n, which was 1,000. Alright, so let's get this little part here calculated first. So 2.33 times that is, actually, need to use my calculator here, oops. 2.33 times square root . Alright, 0.0 Okay, 0.0167. So let's just go with 3 decimals since this one over here is at 3 decimals. So this right here is like my margin of error, ME, margin of error. And so what is my interval? So what's my interval? So I need to finish it up by doing 0.055 plus 0.017 and 0.055 minus 0.017. So when you do that, you get a low number and a high number. And the low number is 0.038, so about 3.8%, and 0.072 for about 7.2%. And so what does this interval mean? So this is my interval. And so interpret what this means. So what does that mean? It means that we are 98% confident that this interval contains the true proportion of kids who want to be a doctor. So it contains the actual proportion of kids who want to be a doctor. Running out of room. Got it. Okay. So somewhere in this interval, we're 98% confident that somewhere in this interval, based on our sample, the best that we could do, somewhere in this interval, it could be at 3.8%, it could be at 7%, somewhere inside there is the actual percentage. Like we have no way of knowing unless we surveyed every person, every kid under 12, but to our best of our understanding, it's somewhere inside of there. All right, so that is confidence intervals. So what I want you to do is there's a worksheet that I want you to start looking at and trying, and we're going to work on it on Tuesday. We're going to do another problem note sheet in class, but I want you to look at these and try them out. It's on Schoology as well for those of y'all online, and we'll go from there.